Hi everyone, I'm Ranvir. This talk I'm going to be presenting one of these tools. Right? The talk so far has been incentives to promote decentralization, but the moment you give incentives, people would like to fake their attributes, right? And that's why we need a Byzantine fault-tolerant way to determine whether the location is correct or not. So this talk is about BFT proof of location. Broadly, this is the work under witness chain through researchers working with us, notably Pei Shen, who led this paper. At witness chain, our broader goal is to achieve consensus on physical state. If you think of blockchains, right, they're not they're kind of working in a silo of their own. Their only connection exists in the form of oracles, which can communicate it to the internet. But it doesn't have a connection to the real physical world. And to establish that connection, we're building a whole suite of technologies on which POL is one of them. Okay, so why location? Why did we focus on location? Because at high level, consensus or coordination happens on a rare attribute everybody agrees on. In case of blockchains, it was purely in the digital realm, so it was consensus on time. Time is the only rare attribute. And once you have consensus on time, you can build any sorts of primitives on top of it. For the physical world, what is an analogous rare attribute? And that is location, right? On top of time. You cannot replicate it. And the goal of our protocol is to have a global agreement on where and when things exist. And based on that, you can build a whole suite of applications, decentralized blockchains being one of them. Okay, so why is this a difficult problem? Because if you look at the suite of technologies available right now, forget Web 3, even in Web 2, you do not have a technology that can provide spoofing resistance for location. So if you look at GPS, you can easily spoof a GPS by just feeding in different numbers, time numbers coming from GPS satellites. This can be done at a software level and at a hardware level. Most common techniques used across blockchains is to use IP to determine location. That can be easily spoofed by amateurs by simply using VPN, because it's a lookup on a database. There have been some approaches to achieving this, which typically rely on local beacons. So let's say I want a consensus on location within San Francisco. We'll set up beacons everywhere, and then I'll have a special device that will communicate with those beacons to determine my location, right? But any such applications rely on communication over wireless medium, which has restrictions on line of sight. So I can only communicate to 10 beacons at a time. And for some reason, if those 10 beacons collude, it's just your neighbors, right? You can collude with your neighbors. You'll be able to spoof your location. And this is something that has happened across networks like Helium, which are providing decentralized physical infrastructure, where people had set up nodes across the Pacific Ocean, in the middle of the Pacific Ocean, because it's a scam. Right? Now, to solve this problem, we need to, we have our own constraints, which is we don't want additional hardware to be needed to solve this problem. Because I can give every human on Earth some transmitter, and then I can solve location in some sense. And we need to rely on a global set of nodes so that you cannot collude like a small subset and form like a local cartel, which can falsify locations. So because of this reason, we chose the method over which this location happens to be the internet. And we rely on active measurements over the internet to determine location. Right. Now, there are some challenges with location determination over the internet. In the end, all location determination is just triangulation, fancy ways of doing triangulation. But over the internet, the whole setup works as follows. So you have a prover, we call it Waldo, The solution is where's Waldo, right? But the prover states a location. So in this case, your block producers stated that, okay, they are based in Prague, right? Now, the task of the network is to determine whether that claim is correct or not. And to what level of accuracy can I determine that it's within Prague? The way this works is there are like nodes called watchtowers. Now, watchtowers are any node. They don't need to be trusted. You can just set up a watchtower on your laptop. These watchtowers are tasked with, in some sense, pinging that prover. And we aggregate those things to determine the location. Now, there are several challenges here. First is, you have, because we want to achieve very large scale of these watchtowers, we establish a permissionless network. Now, in a permissionless network, you obviously have untrusted participants, so you can have these watchtowers to be malicious. And obviously, you can have the prover, that wants to prove its location, to be malicious. So you need to deal with some sort of Byzantine fault tolerance over three, or sometimes two-dimensional plane. And you have internet geometry, which is very intricate. So if I tell you the distance, if I tell you that, okay, the latency between two nodes is 50 milliseconds, you cannot just put speed of light over optical fiber or whatever medium to determine the distance between those two nodes, because internet is comprised of of a lot of intermediaries like routers, ASs, and so on. Because of that, solving proof of location can be separated into two different problems. First is you need to solve for internet geometry. You need to learn the embeddings of how delay corresponds to distances over the internet. And you need to apply some sort of Byzantine trigonometry on top of that, which is the proof of location part. Now, we can go into detailed math here. I'll go at a high level for this. But the first task, which is proof of internet geometry, comprises of these watchtowers pinging each other and getting some measurements. So these watchtowers have their locations. They have their claimed locations. They'll ping each other. They'll get some measurements. Now, this will be a pretty sparse metric because we don't want all watchtowers to ping all other watchtowers, because it can get pretty complicated in time. The time complexities would be very high. So we create this matrix and we apply robust matrix completion on top of this matrix. So this matrix is, okay, how much time did it take for a watchtower in San Francisco to ping a watchtower in Princeton? How much time it takes the watchtower in Princeton to ping a watchtower in London, and so on, right? Now, a lot of these measurements can be Byzantine, but robust matrix completion's objective is to remove these Byzantine entries. And it relies on a primitive that this matrix, in some sense, corresponds to distance. And if you create a matrix of distance, it's going to have a low rank. Typically, you can assume a rank 4 matrix for this. And if it's a rank 4 matrix, you have sufficient constraints to filter out Byzantine entries. So we apply that to create this, how much time would it take for a message from location A to reach location B across the globe to kind of learn this embedding. Now that we have this embedding, we apply the proof of location part on top of that. Now,
sorry, just one question.
Go ahead.
Well, what type of Byzantine, if I ask for a ping,
yes,
then I cannot make my response time faster, but I can make it slower. So do you account for that?
Yes.
Or do you account for any ping, I get the precise?
No. We account for it to be slower. So anybody, it can be slower, not even because of Byzantine nature, it can be slower because of some physical constraints.
Okay. So any ping response is a lower bound on the distance, basically.
Yes.
Okay.
Yes. There can be ping responses that, if you are a malicious watchtower and a malicious prover, then you can set your ping to be 0.
Sure. Okay. Yeah.
So we filter out those systems, those kind of collisions through proof of internet geometry, and you apply proof of location to then not filter out, but like create some sort of a common region, assuming that ping delays can be larger, right? So it can be larger between two nodes, but there can be another node at a certain angle to be short.
Could you give some intuition about the magic behind this robust matrix completion? That seems to be very critical.
Yeah. Okay. So let's even ignore robust matrix completion. That was there for like some efficiency purposes. Say that you can measure all distances between, you can do pings between all nodes within our network. If you do that, if you have malicious watchtowers, they would be able to incorrectly give you a ping from, let's take an example. So let's say I'm one of the malicious nodes here. I'm sitting in San Francisco, but I claim that I'm in Denver, right? So I'll be pinged by several watchtowers, which are based in San Francisco, and I can just delay my measurements, my ping with them artificially, right? But I cannot artificially delay the ping between a watchtower in Denver.
Because assuming there's not such a click that allows you to...
Yes. So the task of this completion is just to like expand that to a larger network. So maybe there is no watchtower in Denver, but there might be watchtower in Phoenix, right? Which might give you a different delay, and you won't be able to replicate that delay because it actually took me a huge amount of time for that ping to reach my actual location, which is in San Francisco.
But like, if you know who is pinging you, you can like change the delay to like be in far. So let's say I'm like on local Wi-Fi, and the local Wi-Fi makes like 30 milliseconds like a delay.
Yeah.
So you can, even though if I'm like really in Denver, I can have 30 millisecond delay.
Yeah.
So like if I know like someone from Denver is pinging me, I will not create any more delay, but I will add more delay in San Francisco.
Yeah.
So how you can deal with this?
So that would be classified as an inefficient watchtower. Right? So that the whole task of this is to measure the distances. So that point will lie somewhere over here, right? Which is like very high delay for a very low amount of distance. Right? It will lie on this curve over here and will not actually contribute to making that geometry. Nodes at this boundary sometimes contribute to that geometry. Now, in proof of location, if you are in a setting where your ping is naturally low, let's say you're connected to a geosynchronous satellite, then you won't be able to prove your location. That's a limitation within our system, because it will throw off an error that, okay, this person can be anywhere across the globe. The uncertainty will go beyond a certain bound.
What honesty assumption do you make when you talk? I mean, you have some malicious and some honest responses. Like, how many honest do you need in comparison to malicious responses for this to work?
So it's so there are bounds on. Okay, so we need more than half.
Sure, that's a million.
But there are bounds on the actual matrix completion and bounds on individual directions. So we assume that in each individual direction, like 60-degree radian, 60-degree arc, we have majority of the nodes to be honest. So we need that majority assumption to be uniformly distributed. So if a setup where you have all nodes within the US correct and all nodes within the Europe correct, that won't work. We need majority and uniformly distributed. Yeah.
Can you explain the different lines? Like, what's the difference between the ratio robust curve and the thin robust curve?
Okay, so these curves are taken by some process of elimination. Mm-hmm. So monotone curve is the base curve, which is I'm getting
worse.
It's a worst case scenario because there might be some nodes which have like very high, which will have very low, so very fast responses for a given amount of distance, right? The robust curve ratio means that you're eliminating the best performing So let's say you draw a line over here, and there are some nodes which are performing exceptionally well, which is, again, both nodes are malicious. If both nodes are malicious, they can claim to be half the world apart and give you a very low delay. So let's say there is a node here, delay 2.5 millisecond, but distance to be huge. So it's a ratio way of like, so the elimination happens by the ratio of delay to distance. Right? Binning is something that this work was done a long time ago. So that's something I'm not. That technique is something I don't remember well. So I can get back to you on that.
The main reason I'm curious is because those two curves look pretty far away from each other, the bin and the ratio. You know, so I'm wondering, because they look close in like the beginning, but somehow they diverge. So I'm curious why that is.
Oh, okay. So the curve that we end up using is this one.
Yes.
Right.
That one looks the most correct.
I think the binning. Okay, I remember the binning. So the binning one is you just set a hard limiter to how much the delay should be.
Mm-hmm.
Right. So if your delay is like within less than like a certain amount,
You just exclude it.
you just exclude it because it's going to be fake. Yeah. Okay. So after we have this internet geometry, proof of location essentially does some sort of intersection of the distance regions. Right? So each watchtower will give you a distance of like, okay, this is at max a few thousand kilometers apart, or a few hundred kilometers apart. So you draw that kilometer circle, a distance circle around it. You do that for all watchtowers, right? And then within a particular arc, you do you need to remove some adversarial challenges, right? So there might be an adversarial watchtower over here claiming a distance like this, right? And you need to remove any watchtowers which are computing a distance which is out of the range of the node. Right? So you remove per certain amount of angles, you remove watchtowers that are deemed to be malicious, right? And you do this across the whole 360 degree. It's kind of like quorum intersection, but you're doing that quorum intersection at each individual arc. But okay, for simplicity, you can just say that, okay, this is just, you get a lot of circles from this, right? And then you find an intersection of those circles. The intersection of that circles is going to be the uncertainty region of that node. Okay? Okay, perfect. So that gives you the location uncertainty of the node. If the node lies within that intersection, great. Then you look at what your metric of a correct location is. This protocol will only give you the uncertainty radius of the particular node. So you can say that, okay, this node is within San Francisco, within a circle of radius 100 kilometers within San Francisco, right? And it's up to the protocol to determine what they set that boundary as. So there are some limitations of this approach, which is if you look at the uncertainty of different number of provers, so on this axis, it's how big that intersection turns out to be, and on this axis is for like what percentage of nodes you tested. So the good news is for a large number of challengers. So this was tested for 450 challengers. There's old data how we have 6,000 nodes in the network. For 450 challengers, you can achieve an uncertainty of 100 kilometers for almost 43% of the nodes. So for 43% of the nodes, at a low density of 450 nodes across the world, you can give city level accuracy, right? If you increase this curve will shift like this, which is great. But there is a fundamental limitation because we are relying on internet, right? So even if we have 1 million or 1 billion challengers using this, we'll be able to achieve city-level accuracy for most of the nodes, but we cannot go to centimeter-level accuracy. Right? For that, you need like some wireless medium. The reason why we can't do that is a fundamental limitation of the internet, of the packet routing protocols that are used over there. But you can solve for that by layering in different other solutions, like image to location, RTK, and so on. Okay, I think that concludes the talk. We use this location data for. So I started this by saying that we do it for consensus on physical location. So what that means is, for physical world, you just need 3 things. You need when an event happened, where it happened, and what happened during the event. So you just need an additional component of a sensor to collect that data and attest that it was at that location for it. The sensor can be like a TE sitting on your phone or whatever. And you can essentially run the world as a state machine, right? So take a photo. That's an observation at time t, observation at time t plus delta t. You will see the difference. That's the transaction in the physical world. This is what we want to achieve, but like this is going to take a lot of high density observers to achieve this. Okay, so what can you build using this proof of location? Well, since we're in the spirit of this session, you can achieve some level of MEV resistance based on all the approaches that we have discussed so far. Also, intuitively, if you just add some latencies to nodes which are at advantageous positions, you can achieve some MEV reduction. You can have verifiable decentralized networks, also the topic of this session. One reason why this was, motivation why this was developed was for infrastructure deployment, where there were a lot of decentralized physical infrastructure networks that were coming up, and they wanted to know if their nodes, their base stations, cellular base stations, GPU nodes, GPS miners are deployed correctly. And you can use that, you can use the system to in some sense audit whether the deployment happened correctly. It can be used for insurance, verifiable news, and so on. So with that, I conclude my talk.
You mentioned that with witness chain you have internal security through
Oh yes, yes. So you have these many nodes, right? But you need but you need some civil resistance for these nodes.
Right. So it's used for civil resistance, not necessarily slashing and accountability and so on.
Yeah. So we use it to ensure that it's majority honest. We cannot slash it because, as we discussed,
Internet.
internet is random. So you don't want to slash somebody because they're Wi-Fi out there.
That's
Started
To clarify, so basically you are running the ping measurements between the individual nodes that are the watchtowers. How do you, for example, map it to ball leaders in Ethereum or similar?
So proof of internet geometry was for location to location. So once you have that location to location metric, you can apply that. Same thing even if it's a different node claiming to be in that location.
So basically once you get information about IPs and so on, you are able to...
Exactly.
Sorry, just one more question about the model. So you say, the honest ones are uniformly distributed.
Yes.
And then how are the malicious distributed? Do they have to fix their locations before or after the honest ones are set?
So they have to, so their location, they can set their location anytime.
After the honest locations are chosen?
After the honest location.
So then you need a minimum number of honest nodes, I guess, for this to work at all, right? It's not enough that you have an honest majority. You need an honest majority plus minimum number of honest nodes.
So you need nodes in different directions. So for example, if you're sitting, do I have a globe anywhere? Okay, yeah. So if you don't have an honest node over here, right, we won't be able to achieve enough certainty in this direction, right? But a node in this honest node in this direction would be sufficient.
Again? Where would I need an honest node and why?
So if you don't have an honest node in this plane, right, you will have to rely on the certainty of these nodes in this direction.
Yeah.
Right. Which would be good, it won't be optimal because we won't be able to. So the intersection of these two circles would have very high distance on this, can have very high distance on this
Yeah.
axis. And we need nodes over here to reduce that.
Exactly.
But it can still work.
So that's exactly, I think that's where my question comes from. Like, doesn't that mean that you can't, like, that the malicious node position need to be fixed before the honest node positions are chosen?
We don't do that.
Okay.
But you do have to make some assumption about the distribution of the honest nodes, right? Because if they're like if all the honest
Yeah,
nodes
yeah.
are in like one place,
It has to be.
No, but even if they're like uniformly placed and there's not enough of them, then like there will be places where I can put a lot of malicious nodes and you won't be able to tell.
that
You
is
won't be able to
Yes.
triangulate, and that's
Yeah,
what my
that's-
question
that's-
was.
yeah, yeah.
So you need a global, like we need full coverage. So our metric of decentralization is pretty simple. It is you just need to cover the globe. That's all.
Yeah, because that's why you have a minimum number of honest nodes, or the malicious nodes cannot be chosen after the honest nodes are chosen.
Yeah.
Either can work.
Thank you very much.
Thank you.